Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic, quantum mechanics, quantum numbers, orbitals, and energy levels. Material in this lecture builds upon the previous lectures, atom basics, and atoms, ions, and isotopes. The lecture will begin with a description of the quantum mechanical model for the atom. Central to the model is the quantum numbers, including the principal quantum number, along with the angular, magnetic, and the spin quantum numbers. We will then look at how quantum numbers can be visualized on the periodic table of elements. From there, we will consider the different energy levels of the orbitals and see how the quantum numbers, the periodic table, and the energy levels combine to give us a platform for determining the electronic structure or the electronic configuration of atoms. For those of you who are familiar with the construction of orbitals, you should move to the last part of the lecture by selecting the topics Orbitals on the periodic table, Orbital Energy, and the periodic table. For the rest of us, a heads up. Some of the material in this lecture doesn't really seem to make much sense from our real-world perspective of matter, so do not be too troubled if it seems bewildering at first. It's okay to find the concepts confusing. That being said, let the description of quantum numbers and energy levels proceed to where they are mapped onto the periodic table. That is where the information becomes usable and somewhat rational. The construction of this lecture is to tie everything together at the very end. That is, at the orbital energy and the periodic table sections. Depending on the degree to which your instructor covers this material, the student might not have to master all aspects of the lecture. On the other hand, you might be asked to derive types and orientations of orbitals, and a second viewing of this recording may be warranted. Keep in mind, though, as strange as quantum mechanics seem at first, it is really very powerful in describing many of the physical properties attributed to an element. One more note. Since we will make extensive use of the periodic table of elements during this lecture, it's a good idea to have a copy at hand. Beyond the Bohr model. While Bohr model of the atom gave a quantum mechanical understanding of the atom, it had its limitations. A severe limitation was that it only worked well with atoms containing one electron. That's hydrogen. And while those spherical orbitals were a competent description of that one electron, it did not show the path of electrons in atoms with multiple electrons. In other words, it didn't work well for the other 100 or so elements. A new model was needed, and that is the quantum mechanical model. It was worked out by scientists in the 1920s and consisted of mathematical equations for calculating the probability of finding an electron in a region about or around the nucleus. Equations were very complicated and well beyond the scope of this level of chemistry. Fortunately, these probabilities, which we will call atomic orbitals, can be viewed as forms, shapes, or regions about the nucleus. So, as we move forward, whenever the term orbital comes up, we are really talking about a mathematical solution to equations that model the most likely place to find an electron. The electron is not limited to this region, it is just the most likely place to find it. With multiple electron atoms, we will need multiple orbitals. That is important because an atom like lead has 82 electrons. The negatively charged electrons are attracted to the positive nucleus, but negatively charged, they repel each other. The orbitals provide some order in this chaos. The size, shape, and location of an orbital is determined by its own set of quantum numbers. Quantum numbers provide a way of assigning each electron in the atom to a region or an orbital around or about the atom. Each electron in the atom is assigned a unique value of 4 different quantum number types. That is, all of lead's 82 electrons will have a unique set of values for the 4 quantum numbers. The quantum numbers are called N, L, M sub L, and M sub S, or just S. We will look at each one of them in some detail. And our friend, the periodic table of elements, is a guide for keeping track of the orbitals and the quantum number designate. The first and most important quantum number is called the principal quantum number, or N. It signifies the energy level of the electron. It takes positive energy values of 1, 2, 3, or 4. An analogy of energy levels would be planets in orbit around the sun. That's like an electron orbiting the nucleus. In this analogy, the larger the N, the further away the orbit of the planet is from the sun. A cartoon representation of the atom, highlighting the principal quantum number, has the nucleus at the center and a shell for electrons residing in the n equals 1 energy level. The term shell is used for the orbitals that are found within a particular energy level. For n equals 2, there is a larger shell. Electrons can be further away from the nucleus, and orbitals within that shell will have larger energies. The same follows for the n equals 3 shell. Atoms with an n equals 3 shell are larger than atoms with just an n equals 1 or 2 shell. Smaller shells are nested or located within larger shells. An atom with an n equals 3 shell will also have an n equals 1 and n equals 2 shell. Here's a schematic of the periodic table. On the left of the table, there is usually a column of numbers. These numbers look like they correspond to the rows of the table, but it is actually a little more complicated than that, and we will return to this subject during our discussion of energy levels on the orbitals. For now, we will just say, be careful in treating n like row numbers. Returning to our description of n, within each energy level there are sublevels that designate atomic orbital type. We will get to orbital types shortly. This table is colored by blacks to show how sublevels can be memorized. The practical component of n is in designating energy levels, and that describes the size of orbitals. And to take us to our next quantum number, the angular quantum number, known as L, and it describes the shape of the orbital. L is correlated to n. Let's look at that relationship between L and n and introduce the different kinds of orbitals. After the introduction of orbital types, we will look at each type in more detail. When n equals 1, L has one type of orbital. It is called an s orbital, and it has a spherical shape. The L value for s is 0. The n equals 1 shell has one orbital. When n equals 2, L has two types of orbitals. It has its own s orbital, L equals 0, which is bigger than the one we saw with the n equals 1 energy level. It also contains p orbitals, L equals 1, which are dumbbell-shaped. The n equals 2 shell has 4 orbitals, 1 s and 3 p's. For n equals 3, L has 3 types of orbitals. It has its own larger s and p orbitals, L equals 0 and 1, and it also contains d orbitals, L equals 2. The shape becomes more complex with d orbitals. N equals 3 shell has 9 orbitals, 1 s, 3 p's, and 5 d's. For n equals 4, L has 4 types of orbitals. It has its own larger s, p, and d orbitals, L equals 0, 1, and 2, and it also contains f orbitals, L equals 3. The n equals 4 shell has 16 orbitals, 1s, 3 p's, 5 d's, and 7 f's. Even though there will be n's that are equal to 5, 6, and 7, there will be no more types of orbitals. Each n has its own s orbital. All n's larger than 2 have p orbitals. D orbitals are limited to energy levels n equals 3 through n equals 6. F orbitals are limited to energy levels n equals 4 and 5. Further exploration of the orbital comes with the magnetic quantum number m sub L. It gives the orbital orientation in space. Orientation will become a bit clearer in a moment. Leading with the s orbital type. There is only one type of s orbital, and that is spherical. The magnetic quantum number is 0 for the s orbital. We have seen that even though there is one spherical type, that each energy level has its own s orbital. They will, however, differ in size. When n equals 1, as mentioned previously, there is only the s type of orbital, and it's called the 1s orbital, where 1 is the principal quantum number, n, and the s is the orbital shape. For n equals 2, there is also an s orbital. It is called the 2s orbital. Note that while it is also spherical, it is larger than the 1s orbital. The n equals 3 energy level also has an s orbital. It is called the 3s, and it is spherical and larger than the 1s and 2s. It's important to understand that the orbitals will exist simultaneously for all atoms at the n equals 3 and higher energy levels. That is, the 1s orbital is closest to the center of the atom, the 2s is larger and encompasses the 1s. The 3s is even larger and contains both 1s and 2s. In other words, the smaller orbitals of a type are nested within each of the larger ones. We could continue this pattern of larger and larger s's down the periodic table with n equals 4, 5, 6, and 7. But let's look at the next type, the p orbitals. There are 3 types of p orbitals, and they are dumbbell shaped. There's a magnetic quantum number for each of the 3 orbitals. That m sub L describes the particular orientation in 3-dimensional space of its orbital. Without going into too much detail, the 3 orientations are designated by m sub L equal to -1, 0, and +1. As mentioned earlier, the energy level n equals 1 does not have p orbitals. Energy level n equals 2 and higher do. Looking at the p orbitals for n equals 2, we have the 2px orbital. It's called px because it is oriented along the x-axis on a 3-dimensional graph. Compare that to the 2py orbital, same shape, but is oriented along the y-axis. And finally, the 2pz orbital aligned along the z-axis. Now, there's not really an x, y, and z axis in an atom. The x, y, and z are used to show how the orbitals are oriented in relationship to each other. As we see when we combine them on the same axis, that they are perpendicular to each other. That is, that they meet at 90 degrees or square angles to each other. One can think of their meeting as that of a corner where 2 walls meet the floor. That orientation is what the magnetic quantum number brings. If we were to look at the energy level n equals 3, we would also find 3 dumbbell-shaped p orbitals. Presented here is just the 3pz. 3p orbitals will be larger than 2p. As a demonstration, pictured here is the 2pz orbital nested within the larger 3pz orbital. Same orientation, same m sub L, but different sizes, different principal quantum number n. A similar argument could be made for 3px and 2px, or 3py and 2py orbitals. Actually, a similar argument can be made for 4pz surrounding 3pz. Bottom line, the larger the n, the larger the orbital. Keep in mind that we are trying to assign a region or regions about the nucleus that have higher probabilities of finding an electron. And with all this overlap of orbitals, it should not be surprising that most, if not all, the area around the nucleus will have assigned to it one or more orbitals. The student is not expected to know what area has what orbital. It's more like having an awareness that there are areas within the atom that are assigned to orbitals. Students are generally asked to identify the shape and orientation of the s and p orbitals. Not so much for the d and f orbitals. We will give them a little look nevertheless. There are 5 types of d orbitals, and they have more unusual shapes. We will simply refer to them as having multiple lobes or multiple lobed. The 5 m sub l quantum numbers for d orbitals are -2 or +2, that's plus or minus 2, plus or minus 1, and 0. D orbitals first appear in the n equals 3 energy level, and each of those 5 magnetic quantum numbers assign a different orbital orientation in space. They also assign a different shape. Here's a look at the 3 d orbitals. The important facts to remember about the d orbitals is that they first appear in the n equals 3 energy level, and that there are 5 of them. Rarely, if ever, do the shapes of the 7 f orbitals come up at this level of chemistry. Multiple lobed is a good general description. The 7 m sub l quantum numbers for the f orbitals are plus or minus 3, plus or minus 2, plus or minus 1, and 0. They first appear at the n equals 4 energy level. The f orbitals really show that they spring from mathematical equations. This single 4f orbital should suffice to demonstrate that multiple lobe shape that f orbitals take. The important fact to remember here about the f orbitals is that they first appear at the n equals 4 energy level, and that there are 7 of them. The last of the quantum numbers is the spin quantum number. It is referred to as m sub s, or just s, and it assigns to an electron a property called spin. The spin can have either a positive 1/2 or negative 1/2 value. Simplified as tiny spheres, we can consider the electron as spinning around on its axis in one direction or the other. The positive and negative values distinguish direction. Spin is important because while these negatively charged electrons repulse each other, they seem to be better able to share a space when one has a positive spin and the other a negative spin. Paired spins. This pairing of spins is found in a foundation rule used in determining the electronic configuration of atoms, the Hun rule. It's a recognition that when we start assigning electrons to orbitals, that we will be limited to 2 electrons per orbital, and that the electrons must have opposite spin signs. Often, arrows are used to designate an electron with a positive up or negative down spin. That's our introduction to quantum numbers. And it's a lot of new and strange material. So let's review it, look for patterns, and see how the periodic table can help us recognize and hold those patterns. We will review by number of orbital orientations. That's how many angular quantum numbers there are for a given orbital type. Also, orbital shapes, the maximum number of electrons that an orbital set can hold, and at what energy level does that orbital type first appear. Starting with the s orbital. There is only one type of s orbital, and it is spherical. According to Hun's rule, each orbital can hold up to 2 electrons. Therefore, the single s orbital can hold a maximum of 2 electrons. The first s orbital appears at the energy n equals 1 level. onto the p orbitals. There are three orientations of the p orbitals. The p orbitals are of a dumbbell shape. The three orbitals are perpendicular to each other. That is, they meet like the corner of a floor and two walls. Since there are three p orbitals and each can hold 2 electrons, a set of p orbitals can hold a maximum of 6 electrons. The first set of p orbitals appear at the n equals 2 energy level. D orbitals. There are 5 orientations of d orbitals. Here we'll just refer to them as multi-lobed. Hund's rule says that each of the 5 d orbitals can hold up to 2 electrons for a maximum of 10 electrons per set. The first set of d orbitals is found at the n equals 3 energy level. And finally, the f orbitals. There are 7 orientations. Like the d orbitals, we will consider them as multiple lobed. Finishing up, 7 orbitals can hold up to 14 electrons, and we don't find f orbitals until the n equals 4 energy level. As for patterns, we see that as we move from s to f orbitals, the number of orientations found for the different types changes by 2, yielding odd numbers 1, 3, 5, 7. If we multiply that odd number by 2, that is using the Hund's rule of 2 electrons per orbital, the pattern moving from s to f orbital changes by 4, 2, 6, 10, and 14. This pattern fits right onto the periodic table of elements. And finally, we see that with each new principal energy level comes a new type of orbital. Now, let's take this review table, along with the patterns we highlighted, and map orbitals onto the periodic table of elements. Believe it or not, mapping onto the periodic table is how this jumble of new concepts can begin to make some sense. We'll begin with the 2s orbitals. Remember that the number on the left side of the periodic table is the principal quantum number n. What we're really interested in is how angular quantum numbers, or orbital types, show itself on the periodic table. We see that the s orbitals can hold a maximum of 2 electrons. Our first mapping comes from recognizing that there is a block of 2 columns on the left side of the periodic table. We will call this the s block. As we progress into developing electronic configurations for atoms, the naming of groups of columns will become clearer. The s block can be subdivided by principal quantum number. The first 2 elements of the s block, hydrogen and helium, are at the energy level n equals 1. We can treat helium as if it was sitting next to hydrogen for this demonstration. We will call this first subblock of the s block as the 1s orbital subblock. We can continue this trend by naming the 2 elements beneath the 1s designation as 2s, since the elements are in the s block and at the energy level n equals 2. The same argument can be made with the principal energy levels 3 through 7. 3s, 4s, 5s, 6s, 7s. That's the s block with its subdivisions. Reproducing the s block on the periodic table begins with locating the first subblock, 1s. Once that is done, the rest is really just counting down by rows. Continuing mapping the review onto the periodic table, we will consider the p orbitals. There are 3 orientations of the p orbitals, which means a set of p orbitals can hold a maximum of 6 electrons. Looking at the structure of the periodic table, we see that there is a 6-column chunk on the right-hand side of the table. These correspond to the p block. The p block can also be further divided in the same manner as the s block. That is, by relating the set of p orbitals to their principal quantum number n. The 6 elements in the first row of the p block are in the n equals 2 energy level. These are called the 2p orbital block. remember that there is no p orbitals in the n equals 1 energy level. We can use this same mechanism for labeling the orbitals in the p block as we did for the s block. Beneath the 2p will be 3p, 4p, 5p, 6p, and 7p. Again, in describing p block, the most important feature is recognition of the first subblock, 2p. On to the d orbitals, which we will note begin at energy level n equals 3. There are 5 orientations of the d orbitals, holding a maximum of 10 electrons. This happens to be the number of columns in the transition metals. We will call them the d block. There are 10 elements in the first row, which we will call the 3d orbitals. Now, getting just a little bit ahead of ourselves and trying to head off some confusion, we see that the 3d orbitals look like they are in the n equals 4 row. This point will be discussed in further detail when we talk about the relative energy levels of the orbitals. For now, we will just note that starting at the 3d orbitals, the energy level n on the left side of the table will not strictly refer to the energy level of all elements of that row. It's an energy thing. However, the same pattern of increasing one energy level by going down one row, like we saw with the S and P blocks, will also hold with the D blocks, meaning that there's a 4D, 5D, and 6D orbital subblock. There is no 7D, and our table is taking shape. Onto the F orbitals. We see that the 7 orientations of F orbitals can hold a maximum of 14 electrons, which corresponds to the 14 columns of the F block. The first row represents the 4F orbitals, and the next row the 5F. Here we come to another feature of the table that requires some explanation. First of all, to keep the table from being too long, the elements of the F block are kept beneath the table and not inserted where they actually belong according to their atomic number. The 4F block elements really begin after the 6S subblock. Same pattern holds for the 5F orbitals. It starts after the 7S subblock. Let's take a closer look at how the 4F subblock fits into the table. Take a peek at your periodic table. Follow the atomic number of cesium and barium in the 6S subblock, 55, 56. But to get to atomic number 57, one has to go down to the start of the 4F subblock for lanthanum. It is not until the atomic number rises through all 14 elements of the 4S subblock that the count of atomic number goes back to the main table with 71 of the 5D element lutetium. And as we saw with the d orbitals, the F orbitals do not look like they begin at the energy level n as seen on the left-hand side of the table. This further highlights the danger of assigning the value of the principal energy level n to the whole row of elements. So why do 3D and 4F orbitals start where they do? That will be our final topic of the lecture, which we will get to as soon as we reduce the effort we made in overlaying the orbitals on the table to just 3 starting pieces of information, which will allow us to recreate this very useful version of the table. The first piece of information is the identification of the orbital blocks on the table. To reiterate, S, P, D, and F blocks on the periodic table follow the maximum number of electrons that orbital type can hold: 2, 6, 10, 14. Looking at just the basic shape of the periodic table, we note that there are 2 columns on the left-hand side coinciding with the maximum number of electrons an s orbital can hold, S block. There are 6 columns on the right-hand side coinciding with the maximum number of electrons that a set of p orbitals can hold, p block. There are 10 columns of the transition metals in the middle of the table, coinciding with the maximum number of electrons a set of d orbitals can hold, d block. And the 2 rows under the table are the f block, coinciding with the maximum number of electrons a set of f orbitals can hold, f block. The second piece of information is the energy level n that the different orbital types first appear. The s orbital first appears at energy level n equals 1. Begin the s block with 1s. The p orbital block first appears at energy level n equals 2. Begin the p block with 2p. The d orbital block first appears at energy level n equals 3. Begin the d block with 3d. Note that if we were strictly looking at the energy level designation on the left-hand side of the table, we would be calling it 4d. Tempting, but that would be a mistake. And finally, the f block first appears at energy level n equals 4. Begin the f block with 4f. It too looks like it begins at a different energy level. The last piece of information we need to complete the table is that from these 4 first appear positions, 1s, 2p, 3d, 4f, we can move down the table row by row, keeping the block designation and adding a 1 to the n value. When the lecture is over, try to repeat this overlay of orbitals on your own table. It is a skill that will pay off repeatedly in the future. Our final task is to rank these orbitals in terms of energy. Ranking the orbitals is an essential component of assigning electrons to their proper electronic configuration in an atom, which is what the orbitals are all about. The nice thing about this task is that the periodic table has already ranked the orbitals for us. So on to a discussion of relative energy levels. Relative in this context is the energy of one level compared to that of another level. In other words, we will be ranking the orbital energies from lowest to highest. We will first need to introduce an important principle in the assignment of electrons to their proper electronic configuration in an atom, and that is where the ranking of energy level comes into play. And that principle is the Aufbau principle. It says when assigning an electron to an atomic orbital, use the lowest energy orbital. In other words, build from the bottom. And when that orbital is filled, go to the next lowest energy orbital, and then the next lowest, and then the next lowest, and so on and so on. There are a couple of ways of ranking the orbitals by lowest energy. We will look at a common application, the one often used in many textbooks, that shows how to come up with the right order, or ranking, though not why. We will then see how that ranking maps right onto the periodic table as we just labeled it. For the first procedure, begin by listing out orbitals as a function of their principal and angular quantum numbers, n and l. For n equals 1, L has one orbital type. List out 1s. For n equals 2, L has 2 types of orbitals. List out 2s, 2p. For n equals 3, list out 3 types of orbitals. 3s, 3p, and 3d. For n equals 4, list out 4 types of orbitals. 4s, 4p, 4d, 4f. We can do the same with 5, 6, and 7. And removing orbital types that are not on the table. Note that all the s orbitals are drawn in a column, as are all the p's and d's and f's. This process of ranking is one of drawing arrows from right to left and at an angle down and across the list of orbitals. Again, this doesn't explain why orbitals have relative energies that they do. It just gets the order right. The first arrow passes through the 1s orbital. It is our lowest energy level orbital. Let's begin a list of orbitals that arrows have crossed through. the orbitals will be listed by increasing energy. The second arrow is parallel to the first. It only goes through 2s. The next arrow goes through 2p and then on to 3s. And on our list, we include 2p and 3s. The fourth arrow goes through 3p and 4s. It does not go through 3d before 4s. The reason here is that as energy levels get larger, the difference in the energy between orbitals gets less and less. So by the time we get to n equals 4, one of its orbital types, 4s, is actually lower in energy than one of the n equals 3 orbitals, the 3d. The next arrow picks up the 3d before moving on to 4p and 5s. This arrow selects orbitals in 3 different energy levels. The sixth arrow goes through 4d, 5p, and 6s. The next arrow selects 4 orbitals, 4f, 5d, 6p, and 7s. The last arrow finishes off the orbitals on the table with 5f, 6d, and 7p. While the arrow application does get the correct ranking of energies between orbitals, it is probably too cumbersome to use on a regular basis. A much more accessible means is to use the periodic table and the listing of orbitals we created earlier in the lecture. We can create the same ranking list by simply reading out the orbitals as they appear on the periodic table. That is, calling out each orbital as we move across and then down the table. Read them like a book. In this demonstration, we will read out the same groups of orbitals that the arrow application gave us. And that's starting with 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and 5f, 6d, and 7p. So if we can assign the orbital blocks onto the table and then just read out the orbitals like a book, we will have taken this very strange set of atomic features and mapped it onto the periodic table of elements and formed a very usable organization of quantum numbers. We can tie our development of orbitals and their relative energies to the topic of the next lecture, electronic configuration, with this stratified diagram of the orbitals drawn as boxes and ranked by energy. Lowest energy orbital on the bottom, 1s, and highest energy orbitals, 7p, on top. From 1s, we add 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on up to 7p. There is one box representing one type of s orbital. That type first appears at the energy level n equals 1. There are 3 boxes representing the 3 types of p orbitals. That first appears at the energy level n equals 2. There are 5 boxes representing the 5 types of d orbitals. This type first appears at energy level n equals 3. There are 7 boxes representing the 7 types of f orbitals. This type first appears at the energy level n equals 4. Filling the representative orbitals with electrons comes in another lecture. Recapping this lecture, quantum mechanical model of the atom. The model is based on mathematical equations for calculating the probability of finding an electron in a region about the nucleus. Probabilities, referred to as atomic orbitals, can be viewed as forms or shapes or regions. Quantum numbers provide a way of assigning each electron in an atom to a region about the atom. Actually, assigning electrons is the topic of electronic configuration lecture. The first quantum number is the principal quantum number n. It is the energy level. We refer to all orbitals within an energy level as shells. Angular quantum number L describes the shape of the orbitals. S orbitals are spherical, P are dumbbell-shaped, and the D and F orbitals are multi-lobed. The magnetic quantum number, M sub L, gives the orbital orientation in space. There's 1 orientation for S orbitals, 3 for P, 5 for D, and 7 for F-type orbitals. The spin quantum number, M sub S, or S, assigns to an electron a property called spin. It's either plus 1/2 or minus 1/2. That's important because the Hahn rule says that any single orbital can hold up to 2 electrons, but their spins have to be opposite or paired. Energy levels of orbitals can be determined from the periodic table by recognizing where 1s, 2p, 3d, and 4f are and filling down the table. From there, one reads the table from left to right and then down a row. And that concludes our lecture. It certainly contains a strange mixture of new ideas, but they map onto the periodic table pretty well. To incorporate these new ideas, practice an Aufbau. That means build up.